So now let's draw an analogy between the work done in a gravitational field versus the work done by the electric field. So the reason we can draw this analogy is that they're both uniform. Your gravitational field G, which we didn't normally talk about in mechanics, but again is analogous where you multiply G times your mass to get a force, that this points in the same direction everywhere by the surface of the Earth and has the same magnitude everywhere by the surface of the Earth. The electric field, when it's uniform, is going to have the same properties by definition. Now note that if we have a uniform electric field, we can assume that we're inside a parallel plate capacitor, since that is the only type of object we've learned about that really creates that uniform electric field. Or we could define a single plane of charge, but there are a few reasons why that's a little less elegant to do. So right now we're going to talk about being within a parallel plate capacitor. So you know that if you drop a ball in your gravitational field, that the potential energy that it has from being at some height is converted to kinetic energy as it falls down. And we would say that gravity does work on the ball because we see that change in kinetic energy. So in this case, we can say that the electric field does work on the particle, and a positive particle falls in the direction of the electric field. We'll talk about what negative particles do in a second. But so this is really analogous in that if I let a particle go right here, it's going to accelerate to the left. And you know that since this just has Q on it, that the force it's going to experience is in fact going to be constant because our electric field is constant. So we have a constant gravitational force in this scenario, a constant electric force in this scenario. So we can use conservation of energy as well, and we're going to see that the equation is going to look very similar for the compared to the gravitational field. We said that in this case, potential energy is equal to mass times gravity, so that was our force, times the height. And here we're going to say that it's again this force, Q times E, times the distance we are from the negative plane. The negative plane, notice here, serving as our zero, just like the ground does here. So to kind of talk through what that math looks like, we again say that the force is equal to Q times E, and that these are vectors. So we're going to take that into account when we do this dot product here. And remember that this is only for a uniform field. I point that out because subsequent videos will do other types of fields. So just like in the case of gravity, we're going to take our force, now it's QE, and we're going to look at the distance that it goes across, and we're using S here. So now note that S is again being measured horizontally from the negative plane, and we are going to be talking about a positive particle. So for simplicity, think about Q as being positive. And again, when we take the magnitude here, we just think about the distance. So again, we go back and we relate our change in potential to the negative of our work done by this configuration. And again, remember here that the potential energy is due to our system. So that's our point charge interacting with our parallel plate capacitor. So in the end, we see that our final minus initial potential energy is just Q times E times the position, this distance from here, final minus the same thing, but with initial. And so we can say that the potential energy due to the this electric interaction here is due to whatever my potential is here, right? This U initial, and we'll talk more about it, is here, and then Q times E times S, where S is the distance you are from this plane. So again, it's going to be important that we really define what is the potential at that negative plane, and then we're measuring the distance from that plane. So what impact is the sign of the charge going to have? Well, we said that a positive charge, we're actually going to see it fall to the left towards, in this configuration, the negative plane. So it always falls towards the negative plane. You then have to figure out, is that on the left or is that on the right? And that's falling in the direction of the electric field. So if it's traveling to the left, we say that its potential energy is decreasing and its kinetic energy is increasing. That's it heading down. On the other hand, we could give it an initial velocity to the right, and we see that it's going to slow down. You should be able to think through the fact that since your electric field is to the left, we're actually going to have a force to the left. So it's going to slow down. As it's slowing down, we say its kinetic energy is decreasing, so its potential energy is increasing. Again, this is all similar to mechanics, but now due to electric fields and electric forces. Now imagine instead that we're going to have a negative charge. Now, if our electric field is to the left, that means that our force is actually to the right. And another way you can think about this is that our negative charge is going to be attracted to the positive charge. So if our negative charge is initially traveling to the left, it's actually slowing down. Its kinetic energy is decreasing. That means its potential is increasing. So for a negative charge, and I like how the book talks about this, the field direction is actually uphill, right? Remember that the force points away from the electric field direction. So this is one thing that's a little bit tricky, is that you have to think about potential and kinetic energy in terms of the sign of the charge, not just the field direction. So if our negative charge is heading towards the positive charge, there's a force pulling it in that direction, it's accelerating. That's the same thing as potential energy decreasing, kinetic energy increasing. So what if we compare a proton versus an electron? And this is something where you have to really stop and think about what's happening. Now we can place them in the same parallel plate capacitor. That means that you have the same field because the parallel plate capacitor creates the field. Now a proton and an electron has the same magnitude charge, but they have opposite signs. And we're going to have actually the same conversion, that our change in potential energy is going to be equal to our negative change in kinetic energy. Keep in mind that there is a sign here, so a decrease in one is an increase in the other. Well, what if we let them go from rest, both in the center? We know that our positive charge is going to go to the left, and our negative charge is going to go to the right. Why is that? Well, our electric field is pointing to the left. And it is uniform, but I'm just going to draw one field line. So our positive charge goes with the field, our negative charge goes away from the field. So we have different directions. Now the other thing to think about is that these have different masses. The proton is about 2,000 times heavier than the electron. So even though they have the same delta K, and they're going to have the same delta U, in this scenario, since they're let go in the center, we can think about the change in position, right? The magnitude of delta S is actually going to be the same. And since E is the same, we are literally going to have the same delta U. That's true because we've let it go in the center. But the speed that it has when it hits the plane is actually going to be different since these have different masses, and that goes into your kinetic energy. So please be careful about that. So last, let's think about a visual representation, and that is the energy diagram. Again, we met energy diagrams in Physics 202, so if this quick review doesn't make sense to you, please make sure that you go back and review some Physics 202 videos about this. The idea of an energy diagram is that we draw one horizontal line that is going to represent our total mechanical energy. We then draw another line, which is our potential energy. Our horizontal axis is then going to be position, and our vertical axis is energy. Note that in this scenario, we are also showing our parallel plate capacitor, just so that this position really makes sense. So when you have these two lines, this mechanical energy is about your system. So that has something to do with your starting values of, for instance, where you let your object go, or the speed that it has at the beginning, or both. So this is specific about your object and its initial parameters. Again, that potential energy is just about the system that it's in this case, the parallel plate capacitor. So if you're at a given location here, what we actually then have is that it has this much potential energy, and so the difference between the potential energy and this total energy line is your kinetic energy. So if you get up to this point where they intersect, that's the turning point. Your kinetic energy is 0. That's where its potential energy is equal to its total energy. So it's turning around and coming back. So in fact, this region is forbidden because the amount of potential energy that it would have in this region, given by the blue line, exceeds the brown line. That means that it doesn't have enough energy to ever be here. So our particle can only be in this region. Obviously, if we had more mechanical energy, it could be here. So that's the basics of interpreting an energy diagram.